Alright, let's talk about stochastic resonance in an op-amp based circuit. This summer, 2021, I had to switch parts because the other part I was using wasn't available because it was too expensive due to the chip shortage. But I had a lot of these chips on hand, and so that's what we're going to use. You'll notice that I tried to make all the node names similar to the names that the ADLM 2000 uses. But in this case, when I'm doing extractions, it doesn't like numbers. So the channel to measure this will be 2+. The channel to measure the noise will be 1+. And then you'll have 2- and 1- for the other side of the channel. You need to hook those to ground because the M2K is a truly differential measuring device. This here is it just puts the frequency as a time constant so that I can extract it. And so I'm extracting the mins and the maxes because I have to save the data as a WAV file, which will put it into even time steps. But you lose the magnitude information. It's relatively right, but it just puts it in integers. So I have to extract the mins and the maxes to scale it to make sure that in Python I can process everything. Okay. But pretty much we have the noise source. S is just a scale factor. The larger S, the larger the RMS value. 50K accelerates the white noise source, and so this is matching fairly well with experiment right now today, and we'll do it. And we have a transient. Other things, the options plot window size means there's no compression, and the number of digits is 15, gives us an accurate simulation. So I've already run the simulation, and you can see that I'm running it for a fairly long time. We can't actually measure for a second, but you do get some nice clean data. All right, and to double check, we just control left clicked on the scale noise, and we get an RMS of 248 millivolts. So that we'll use that to check later. I'll do a quick zoom here. And you can see that it's turning off and on. The green is the one with the forcing function, and the blue is the one without the forcing function. So we can take the FFT of that, and we can see that we are getting some stochastic resonance because there's a clear peak here at 1 kilohertz, right? Now the noise, its frequency information, it's about flat right out about to 10K or 20K. So when you're with noise, you need the standard deviation, the RMS of the voltage, right? But then you also need a measure of the frequency range that the noise is at as well. You need both really to be able to repeat anybody's work, and I've actually had a heck of a time doing that. So what I've got is some Python code. It's a little bit ugly, but it's working, and it will take those WAV files and process them, right? And so we have something where we prep the data, which is basically finding the peaks and the frequency the peak occurs at for signal to noise ratio. We calculate the power spectrum, finding a peak. We have a Gaussian and Cauchy distributions. We fit to Cauchy because we're going for Lorentzian. All of this is designed to extract these values automatically from LT-Spice, where if you were to view the error log, you could see that RMS is 0.248 mins and maxes, and the amplitude and the forcing function. That way it passes all into Python. So we scale the data. We read, I should say, we read in some constants from the log file. I should point this out. So this is reading the log file. If you want to do this, you've got to change the path to your log file or it'll choke. All right. Then we read in the data and you got to change this path, right, to make it run. Otherwise it won't work. So here we calculate the power spectrum, right, without the forcing function and with. Then we put it into RMS because LT-Spice gives the magnitude of the FFT in RMS, and Scopy does as well. And then here we just calculate some curve fitting parameters, or we get some parameters which then we can curve fit. And then what we do is we found the maximum value of the power spectrum density, which happens to be in this case at 1000 Hertz. And then you divide it by the fit at that. So you're getting the signal to noise ratio. I'll show you in the plot later. And then we have a lot of other plots and we print things out. So if we just run it, okay. Now here's the data, which kind of hard to see, but it's actually useful to make sure you haven't made a mistake. But you can zoom in and see what's going on. So here's the data without the forcing function, and we curve fit, and the full width half maximum is 2.3 kilohertz. But over here we're calculating this peak to this value right here. We curve fit it even with that peak. That peak is only one value there, so it doesn't really affect the Lorentzian curve that much, right? And we get a signal to noise ratio of 16.46. Our peak here is 1.25, which compares somewhat okay here, of 1.8, and I believe in that algorithm it's like the power spectral density is like the FFT, but it is not the FFT. But there's a peak at 1000 and the RMS value is pretty close. Okay, coming back here, right, this is just a Schmidt trigger where this is a triangle wave, and let's just run this and we see that's the input, this is the output, and we can see our two trigger points, and I believe I calculated it in the lab manual. It's about 0.6 in simulation, this hysteresis width, right? Your sine wave of the forcing function has to be less than this, otherwise it'll just drive it. It's not really amplifying, it's just driving the output. And the noise, the peak-to-peak noise, has to be just on the other side of it. If it's inside and too small, right, I'm just wiggling it back and forth, the circuit won't work. Now, a trick is that rather than build a circuit and test it with and without the forcing function, in Scopy, you can actually set the voltage source to 0. I've tricked it by setting it to a nano, right? But then when it's time to put in the forcing function, you just go back and do that. And you can see that now when I've added a forcing function, those trip points are moving around. So this is a non-linear device, so superposition doesn't really apply. But if this were tied to 0 and this were the input, it would be a non-inverting Schmidt trigger. And so combined, if this oscillates around, this is changing those trip points. And when these frequencies align, you can get stochastic resonance. So right here, this should give us an RMS of 248. The noise rolls off about 20 kilohertz. The amplitude of the forcing function is 0.1, and the frequency is 1K. So now we go to Scopy. Okay, and I have I'll have a file here where you can load in all the parameters. All right, but our power supplies are on. Let's go to signal generator. You have to load, if you click on buffer, you can go into that directory. Again, I'll provide all that. And you just load in this noise source, right? And then you're setting the amplitude to 1.7 and the sample rate to 50 kilohertz. It'll come in at a different, like 10 megahertz. And to speed and slow up the noise, you just adjust this parameter here. Okay? So it was already running. And here's my forcing function, right? The amplitude, they have it in peak to peak, so it's 200, right? So that'll be 100, like the SPICE simulation, and it's at a kilohertz. But in order to check the full width half maximum, we have to set that to 0. So I don't have to set it to 0 here. I just put it constant. Now that's gone, right? If I go to the spectrum analyzer, eventually this peak disappears, right? But now we go to the oscilloscope and run, all right? We export it, and again, you're going to want to put this in the directory, the correct directory, and you just click on full width half maximum because that's the name of the file. That's so we have SR Scopy full width half maximum, and we just run that, and it'll calculate a signal to noise ratio, but it doesn't exist. This peak, right, it's just noise from the system. It doesn't really exist. Or I mean, it's there, it's just not at 1,000 hertz, which is what we're looking at, right? But you can get the theta value is 0.2418. The signal to noise ratio, like I said, that number is meaningless because there is no forcing function. But here's the full width half maximum of the forcing function is 3.4. Now why is that important? Well, this is for the quartic oscillator, and you have a table of theta in millivolts, signal to noise ratio. Again, it doesn't matter for what I just did. And then the full width half maximum, that's what you would write. And when you plot, and there's a typo here, it's really full width half maximum, the log of it, versus 1 over theta. There's a point where there's a straight line, and you can extract the barrier heights and other things from that. What I suggest is also you can read your RMS right from here, but to change RMS, you come back to channel 1 and you just make it bigger, right? And you make it bigger, you go and measure, run it, and then you're just making a table of RMS versus full width half maximum. So about that. Now, with the forcing function, well, now we turn the forcing. Whoa. Go back to the buffer. It might have forgotten, so we were at 1.7. Okay. Always make sure to go back and see that you're getting the, oops, and it put it at 10 megahertz. Sometimes it does that on you. You got to make sure you're at the right speed. Okay, here we go. And just so you know, if you think I want to get more data and you kind of zoom out, the noise will get smaller because it can't digitize it. The digitizer is limited, so you're stepping over peaks. Okay, so if I zoom in, I can get a decent RMS value here, but then I'm not getting enough time to get a decent plot. And for this example, 5 milliseconds per division, it's pretty good. And now we're going to export it. Now here's the thing. It's the same full width half maximum, except this time there really is a forcing function. Okay. And so our peak, and this is an RMS as well, that's about 1.1. And what were we getting before? You know, it was a little higher in simulation here, but I was able to run the simulation for much longer, right? And so the longer you're able to run it, the cleaner you can make your data. So you would just do that, changing the RMS value. And finding the full width half maximum, changing the RMS value, and finding signal to noise ratio. Now, something I need to point out is that this is a random signal. And let's see, what did we get last time? We had theta 2.51, signal to noise ratio 7.72. Let me export it again. Let me run it again. So you can see these two varied a little bit. So here, this was the same theta because I could extract these at the same time. What you'll have to do when you're using Scopy is extract a chart of theta versus signal to noise ratio and theta versus full width half maximum. All right, and just to recall, the signal to noise ratio is this peak divided by that yellow line. That's what I'm considering the noise. And I'm extracting it with the Lorentzian so that I'm not eyeballing where, where's the noise? Is it here? Is it there? You'll get a consistent result, right, every time. But that's pretty much it. I'm going to write up the lab manual. But this video and these files are everything you need to do to study stochastic resonance. Things that we can do is there's a hysteresis width. We can, how does the hysteresis width again, I'm just hacking it. Change the hysteresis width and do and see what changes. Okay. Now you might think you have to change the hysteresis width with these voltages, but if you look at the equations in the lab manual and on Wikipedia, I can change these switch positions by changing the power supplies. Now the maximum power supply is plus or minus 5, but if I lower them, I can make these smaller. Okay? But the thing is, so probably what I recommend on these measurements from, real measurements is take it 3 times and then average the theta and the signal to noise ratio. Average the theta and the full width half maximum. And then that'll probably be pretty clean and data we can trust. And yeah, even if we all did the same thing, right? We all use the same op amp, the same resistors, same hysteresis, there will be a variance, right? But if we all did it, we would have a lot of data, and that would make our results really rock solid, right? Because we would actually be able to calculate how much things varied, right? Anyway, I hope you enjoy.